Hi. So today we are going to be talking about chemistry. I just want to cover some of the basics, and this is because there is a lot of chemistry in biology. And so I want to make sure we all have the basics in chemistry so we can understand the biochemistry. So maybe you've taken a chemistry class in the past, maybe you haven't. So I just want to make sure that we cover our bases. But today's notes is titled Chemistry. And first, I want to say that everything in the whole universe is made of matter. So everything is made of matter. And matter is made of all the elements. Okay, so matter is made of elements. And as humans, we have organized in a table all the different types of elements. And that table is called the periodic table. Okay, and so let me pull up a picture of that. I know all of you have seen one of these before. They are in every single science classroom. So if you've ever taken a science class, you have definitely seen a periodic table of elements. And so this is a table where all the different elements are organized in a way where they share different properties that they have in common. I'm not going to go into the details of all the different elements, just the elements that are important for biology. And so I'm going to say a couple of things about all of these elements is that matter can be found in 3 different states. And these 3 different states are either a solid, a liquid, or a gas. Okay, so all of these different elements can be found in any of these 3 states. And so usually as you add heat, they go from a solid to a liquid. And if you add more heat, they go from a liquid to a gas. So they can all be in any of these 3 states. They all are at a certain state at room temperature. But again, if you add heat to them, then they'll change into the next state. I want to say that 92 of these elements are naturally occurring. Naturally occurring in nature. And then there are about 20. So about 20 of them are man-made. Okay, so let me move this. So 92 we find in the universe, and then the rest of them are made in the lab. Okay, and we make them in the lab just because we want to see what they look like. They're very unstable, so they don't stay in that state for very long. They quickly degrade into a different element. Okay, another thing that I want to point out is that 6 of these elements are found in all living organisms. So 6 elements are found in all living organisms. And you need to know these. They are carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus. Okay, so those 6 are found in every single living organism on our planet. Of course, there are other elements that are found in different living organisms, but these 6 are found in all living organisms. Okay, and we will talk about the importance of each of these as we go through the different types of molecules. So the way that I remember this is CHNOPS. Okay, it's like a made-up word. And if you just remember CHNOPS, you can remember the carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. Okay, so it's just kind of an easy way to remember. So like on the quiz, when it says, what are the 6 elements found in all living organisms, just remember CHNOPS. Okay, so let's see. I'm going to focus on an atom. So an atom is the smallest thing that, like if you take matter and you break it down to the smallest thing, is called an atom. Sometimes the word atom and element are interchangeable. Usually element means like a lot of atoms of the same kind, and atom just means one atom. So an atom is made of 3 subatomic particles. So atom is the smallest piece of matter. and it has 3 subatomic particles. Okay, and I'm going to go over those 3. The first one is called a proton. And a proton is a subatomic particle, so it's part of an atom that has a positive charge. So it's a particle that has a positive charge. Okay. The second one is called an electron. And an electron is a particle that has a negative charge. Okay, and then the third one is called a neutron. And a neutron is a subatomic particle that has a neutral charge, so there's no charge. So a particle that has no charge, so it's neutral. Okay, and in some classes, you can represent an atom using what is called a Bohr model. Okay, so a Bohr model is a way to represent an atom. So it's a representation of an atom. Okay, it's not really an accurate representation, but it's what we have. So that's what we're going to use. And so basically what I'm saying is that a Bohr model is used to draw what an atom looks like. And so I'm going to draw one atom for you using a Bohr model. Okay, and the atom that I want to focus on is carbon. So I am going to pull in the carbon. Let's see, carbon. This is the carbon from the periodic table. Okay, so this is like one tile. And I'm going to tell you what each part means, and then I'm going to draw a Bohr model. Okay, so so this here, so I'm going to draw this arrow here. Oh, is that an arrow? It's just a line. Stands for the atomic number. Atomic number is what that is. I'll explain what that is in a second. This is the name of the element. Element name. This is the atomic symbol. Oops. Okay, and all atomic symbols are either 1 or 2 letters. And then this last thing down here is called the atomic weight or atomic mass. Or atomic weight. Okay. So those are the different parts of each tile in the periodic table. And so when I draw a Bohr model of each atom, I'm going to tell you where I get the information from based on the periodic table. So my Bohr model, I'm going to make it blue. So what I want to say is that each atom has a nucleus, and the proton and the neutron are in the nucleus. And this number here, this atomic number, stands for the number of protons, neutrons, and electrons, okay? And the proton and the neutron are in the nucleus. So when we draw a Bohr model, we're going to write what's in the nucleus first. So I'm going to say there are 6 protons in the nucleus. So I'm going to write 6 with a P plus meaning it's a positive particle, and P meaning proton. And then there are 6 neutrons in the nucleus. So I'm drawing a picture, and this is in the middle of my atom, and I'm drawing what's in the nucleus, which is the protons and the neutrons. Okay, so we have 6 protons, 6 neutrons. I'm drawing carbon. I'm getting this number from the atomic number. This right here, the atomic mass, comes from adding the protons plus the neutrons. Okay, so 6 plus 6 is 12. So the atomic mass of carbon is 12 for this atom. As you can see, and maybe you've noticed that this is not a whole number, and I'll explain why in a second. But the atomic mass for this atom is 12 because there's 6 protons, 6 neutrons in the nucleus. And the nucleus is what has the weight of the atom. There are electrons outside of the nucleus, but the electrons don't have a weight. They're so minuscule that they don't even count for the weight. So the weight comes from the protons and the neutrons. Okay, so then continuing on to drawing our Bohr model is we have what we call an orbital or a shell. And so the shell goes outside of the nucleus, and it's really the path of the electron. And the electrons can be anywhere around the nucleus. The first shell is a sphere. Okay, so it's not a circle, but it's like a ball. So it's a sphere. And the electron just buzzes around the nucleus and really fast. And you can never see it because it's so fast and they're so small and they're so light. So basically they're buzzing around. And the first orbital in any atom can only hold up to 2 electrons. Because our atomic number is 6, that means we have 6 electrons. So I'm going to draw the electrons as pink. Okay, no, that's not what I meant to do. And so I'm going to, no, hold on. I'm going to draw this like that. So that's 1 electron, and this is the second electron, okay? The first orbital, which is a sphere around the nucleus, can hold 2 electrons only. So I'm going to write that down here. So the first orbital, I'm going to call it shell, but it's an orbital, holds up to 2 electrons, okay? And I made that an E for electron, and I'm going to actually put a minus sign here because it's negative. Okay, so like I put the P plus, that means proton, which is positive, electron is negative. Okay, the second shell can hold up to 8 electrons. Hold up to 8 electrons. Okay, the third shell can hold up to 8 electrons. Okay, and so all the shells after the first can hold up to 8. So the rest of the shells hold up to 8 electrons. Okay, so it's really only the first shell that can only hold 2. The rest of the shells can hold up to 8. Carbon has 6 electrons, and the first 2 are going to be in the first shell. Then I'm going to make another shell, which is the second shell, and it's going to go around the first shell, and this can hold up to 8 electrons. But I have 6 total. 2 are in the first shell, so I'm going to make, that's 3, 4. Oops, sorry. Hang on here. This is 4, 5, 6. Okay, so this is what my Bohr diagram looks like for carbon. Let me just make that a little bigger. Okay. And so I'm just drawing them as like these little dots. Okay. But they're really moving around. Okay. And they're very, very, very far away from the nucleus. In fact, people have said that if you had a football field, the first shell would be the outer perimeter of the football field, and the nucleus would be a penny in the middle of the football field. That's how much space is in between the electrons and the nucleus of an atom. So everything, like all matter, really is just a bunch of space. Okay, so this is carbon, and this is a Bohr model of carbon. You can do this with any of the elements in the periodic table, okay? You just have to know what this atomic number is. Okay, so we've got that atom. It's got 6 as the atomic number. I want to point out a couple more things, and that is that sometimes the neutron number changes. If the neutron number changes, well, that is called an isotope. Okay, so an isotope is when there are more or there are less neutrons in the nucleus, okay, than what the atomic number is. Okay, than what the atomic number says. Okay, these are called isotopes, and these are radioactive isotopes. Okay, so when we talk about radiation, this is what we're talking about, isotopes. And so I'm going to give you some examples of some isotopes. So an example, okay, so carbon, I'm going to write carbon like this, and carbon 12 means that you have a normal carbon that has 6 protons and 6 neutrons in the nucleus, just like I just drew. That's a normal carbon. But an isotope of carbon is, an example of that would be carbon 13. And this one has 7 neutrons. So in the nucleus of carbon 13, nucleus of carbon-13, there are 7 neutrons. Okay, and so this would change to 7, which would then make it a little bit heavier. Okay, there's also a carbon-14, which has 8 neutrons. Okay, so these exist, and these make the element a little bit heavier. So when you see this number up here in the periodic table, and it's not a whole number, what this number is showing you is the average of all the isotopes and the normal elements in the universe. So it's saying that sometimes carbon might have more neutrons. Okay, so that means the weight is a little bit higher than 12. Most of the time it's 12, but sometimes you see carbon-13 and carbon-14. And carbon-13 and 14 are very useful for us as humans because they degrade, because radioactive isotopes, they degrade slowly and at a constant rate. And we can tell by carbon dating, by looking at the carbon-13 and carbon-14 of how long it's been degrading, you can tell the age of anything. So when we see a fossil, we use carbon dating to tell you how old that fossil is exactly based on these radioactive isotopes. Okay, so that's what an isotope is. It's when there is a different number of neutrons. Okay, the next thing that I want to say is that sometimes you have a different number of electrons. Okay, and that is called an ion. An ion is when there are more or there are less electrons, okay, than what the atomic number is. Okay, and this is common. And so an electron is a negative particle. Okay, so I'm going to write that. An electron is a negative particle. And so when an ion loses, an electron, so let's say an electron leaves an atom. So let's say we had carbon here and it lost one of its electrons. That means it lost a negative piece. And so overall, this atom would be more positive, because if we lost this electron, then it would only have 5 electrons, but 6 protons, which would make it more positive. So a positive ion is when you lose electrons. Sometimes it's more than one. So electrons. And a positive ion has a special name, and it is called a cation. Okay, cation. I always associate a cation with cats. I don't have cats, but I think they're really cute. Everybody loves cat pictures or kitten pictures, and so it's a positive thing. So I always remember a positive ion is a cation. Okay, and then, or you could have a negative ion. And this is when you gain electrons. Okay, and so imagine if you had this carbon and you gained an electron, that means you would have 7 electrons, so 7 negative pieces and 6 positive pieces, so you'd be more negative. And a negative ion is called an anion. Okay, so that's a special name for a negative ion. Okay, so that's what an ion is, okay? And then the protons, you can never change the number of protons. If you change the number of protons, you are now talking about a different element. So really, the atomic number in the periodic table is telling you the number of protons, because you can change the different number of neutrons, and you can change the different number of electrons, but you can never change the number of protons. And if you do, you now have a different element. And that happens. Sometimes you lose a proton and now you're a different element. That happens sometimes, especially like in atomic bombs. Okay. So that is the skinny on atoms. Okay, sometimes atoms interact with each other. And when they do, what we say is that they form chemical bonds. Okay, so I'm going to do a different color here. This is a new section of our notes, and we're going to title it Chemical Bonds. Okay, and so this is when the electrons are interacting with each other. So I'm going to say when atoms interact with each other through the electrons. Okay, so the nucleus of atoms never touch. They can't, because there's all these electrons that are keeping the nucleus like isolated. Okay, so when atoms interact with each other through the electrons, This is called chemical bonding. Okay, and there are 3 types of chemical bonds. 3 types of chemical bonds. The first one, this is what we're going to go through. The first one is called an ionic bond. Okay, and we just talked about ions. So an ionic bond is when you have 2 atoms and one atom is going to give up an electron and give it to another atom. Okay, so when one atom gives an electron to another atom, okay, and then when that happens, the atom that is giving away the electron is becoming more positive, and the atom that is taking the electron is now becoming more negative. And now there's an opposite attraction happening because one's positive, one's negative, and they're attracted to each other. That attraction to each other is called the ionic bond. Okay, I'm going to show you an example. Okay, I'm going to show you an example of sodium chloride. Okay, sodium chloride. And if you don't know already, this is your everyday table salt. Okay, this is what we put on our French fries and we love it. It's delicious. Sodium chloride is table salt. And I'm going to, let's see, should I pull in the periodic table? Yes, let me grab the periodic table for us so we can look at it. Okay, so here's our periodic table. I'm just going to put it off to the side here. And so sodium is Na, and that's over here. Okay, and it's hard to see it because I can't even see it. Let me zoom in a little. Actually, I want to zoom the whole table, the whole paper. Okay, so I can't really see that, but it is, let's see, this is 1, 2, 3, 4, 5. This is 5, 6, 7, 8, 9, 10, 11. So the atomic number of sodium is 11, according to the periodic table. Okay, and so I'm going to draw a Bohr model of sodium. Okay, and I said there's 11 protons in the nucleus, and we've got 11 neutrons in the nucleus. And then I'm going to draw the first orbital. And I know, and you should know this now too, but the periodic table helps you tell you how many orbitals you're going to have. If you are hydrogen or helium, you're only going to have 1 orbital because these are the 2 electrons in the first orbital. This second row is 2 orbitals. This third row is 3 orbitals, 4 orbitals, 5, 6, 7. So you can only have a maximum of 7 orbitals. Because sodium is in row 3, I know there's going to be 3 orbitals. So I'm going to go ahead and draw 3 orbitals here. Okay, and I'm going to draw the electrons. And so there's 11 electrons because the atomic number is 11. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's the 11th one. Okay, so I want to point out that electrons are negative, and so they repel each other, because if you're of the same charge, you don't like each other, so you're going apart from each other. So I drew these 2 electrons on opposite sides of the orbital, but they're buzzing around, okay, together. And then in the second orbital, I drew them all, you know, like in the carbon, all spread out, but then I paired them up because I want to point out that it helps you just see if an orbital is full or not. And when the orbital is full, it is happier. It's more stable. So the orbitals want to be full on its outer shell. Okay, and this outer shell here is not full. There's only 1 lonely electron all by itself, and it's not happy like that. So, so now I'm going to draw chlorine. Okay, chlorine is over here. And chlorine is 11, 12, 13, 14, 15, 16, 17. So the atomic number for chlorine is 17. So I'm going to draw chlorine here. I'm going to put 17 protons, 17 neutrons. Okay, and let me draw the orbitals. So I know it's going to have 3 orbitals because it's in the 3rd row of the periodic table. Okay, and so there's 3 orbitals. I'm going to make his electron, him or her, I don't know what she is, he or she is, but I'm going to make chlorine's electrons orange so you can see the differences in the electrons. So there's 17 electrons. So here's one. Oops. Okay, hang on. Okay, here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, oops, 11, 12, 13, 14, 15. I'm going to put 16 here. Oh, and 17 here. Okay. So on the third shell, I have all the orbitals full except for this one is all by himself, him or herself. This electron is all by itself. So what's going to happen is when you have sodium and chlorine come together, this electron is going to happily move over to chlorine. Okay, so this is sodium here. Let me label this so you can see. This is sodium. This is chlorine. Okay, chlorine. And this electron here, so I'm going to do an arrow. Let me make this, change colors. I'm going to draw an arrow here. There's an arrow. That electron is going to move from sodium and go onto chlorine. So I'm going to redraw it here. And here is my electron that's coming from sodium. And I'm going to erase it here. Okay, so that electron's gone. So it moved. So now sodium is happy because its outermost shell is full. And so now it's very stable. And now chlorine's outermost shell is full. And so it's stable. And so because sodium only has 10 electrons and 11 protons, it is more positive. So now it has become a positive ion. So I'm going to put a plus here. So that's how you write an ion. You add a little plus symbol. If it had lost 2 electrons, you would put a 2 plus. If it had lost 3 electrons, you would put a 3 plus. Chlorine gained an electron, so it is now one more negative. And so I'm going to put a negative sign here, okay? If it gained 2 electrons, you put 2 negative. If it gained 3 electrons, you put 3 negative, okay? You never gain more than 3 electrons. Okay, now that we have sodium and it's very positive, and now we have chlorine and it's very negative, they are so attracted to each other because opposites are attracted to each other. That might be true for humans, I'm not sure. But sodium, positive, and negative chlorine definitely are attracted to each other. So this attraction here is what is called the ionic bond. So let me put that here. Here's an arrow, and I'm going to write the attraction between the 2 ions is the ionic bond. So it's the actual attraction. So that love that they feel for each other. It's the love that is actually the ionic bond. Okay? So that's an ionic bond when electrons are being given to the other one. Okay, the second type of bond is called a covalent bond. So this is number 2. Covalent bond. A covalent bond is when one atom, when 2 atoms are interacting with each other and they are sharing electrons. They're actually touching and they're like holding hands because they're touching each other and they're sharing the electrons. So I'm going to go back up here real quick because I just noticed that I didn't capitalize the B and I want to. Okay, back to covalent bond. This is when 2 atoms are sharing electrons. Okay, this is very exciting. And so I'm going to use an example again to show you. And the example that I'm going to use is methane. Okay, and methane is CH4. Okay, and I don't know if you know this, but methane is what your farts are made of. So we all know what methane smells like. Okay, so we're going to draw what your farts are. Okay, so methane is CH4, and what this chemical formula is telling me is that there is one carbon and there are 4 hydrogens. Okay, so I'm going to draw a Bohr model for methane. So carbon that I drew earlier, the Bohr model for carbon earlier, if you remember, has 6, the atomic number 6. So in the nucleus, we have 6 protons and 6 neutrons in the nucleus. Okay, and then, oops, I'm going to draw my circles, my orbits. So, and then from the Bohr model from before, there's 2 orbitals. I'm going to draw pink electrons for this guy. And so, hang on here. Here's 1 electron, 2 electron, 3 electrons, whoops, 4 electrons, whoops, sorry, those are kind of big. 6, I'm sorry, 1, 2, 3, 4, 5, and then this is 6. Okay, so there's 4 electrons on the outside. Carbon is a very important atom for biology because there are 4 free electrons that can easily pair up with other atoms. And so I want to point out in the periodic table, the hydrogen is right here at the upper left. It has atomic number 1. It is the lightest element out of all the elements, okay? And helium is second lightest. And we know it's light because we put helium in our balloons and it floats right up. And hydrogen is even lighter. It's got an atomic weight of 1, where helium has an atomic weight of 2. But hydrogen is what I want to focus on now because it's part of methane. We've got 4 hydrogens. It's got the atomic weight of 1. So I'm going to draw Bohr models for hydrogens and add them to my Bohr model. Okay, so I'm going to make hydrogen blue. No, not blue. I already did blue. How about teal? Okay, so this hydrogen goes here. There's 1 proton in the nucleus, 1 neutron in the nucleus, and I'm going to draw 1 orbital because it only has 1 electron, okay? And I'm going to make its electrons orange, and I'm going to draw the electron here. It's going to be sharing its electron. So now this hydrogen atom is super happy and stable because its 1 orbital is full because it can only hold up to 2. And this orbital here of carbon is starting to fill up, so it's becoming happy. So I'm going to draw another hydrogen here. Sorry about that. Another hydrogen here. Let me scoot that over. And then another one here. I got to scoot that over too. Okay, and then the 4th one here. Oops. Let's put that like right there. Okay, good. Okay. And so each of these hydrogens, let's see, hang on, has 1 proton in the nucleus and 1 neutron, and it has 1 electron, and the electron is going to be shared with the carbon. Okay, so we've got a shared electron here. Whoops. And then we've got a shared electron here. Okay, you get the idea. Let me just make sure my picture is complete. We have 1 proton, 1 neutron in the nucleus of that hydrogen. We've got 1 proton, 1 proton, and 1 neutron in that one. Okay, so this is our Bohr model of methane gas. And so it's a very stable molecule. And because all the outer shells are all the way full. Okay, so what I need to point out is that the covalent bond is right here. I'm going to draw a red circle here. Okay, I'm going to draw a red circle. This right here is the covalent bond. Okay, is where the electrons are being shared. Okay, and so in methane, there are 4 covalent bonds. One right there that I circled, another one here, another one here, another one here. Okay. Okay, so what I want to say next is that this molecule, okay, molecule means atoms that are together through chemical bonds. This molecule is considered a non-polar molecule. Okay, and I'm going to explain that in a second. So let me write this, or I'm going to add this here. So this is another aside. Okay, so here's something else that we have to learn. Nonpolar and polar. So a polar molecule is one that has a top and a bottom. Okay, a molecule that has two ends that are different. Okay, I'll explain this in a second. A nonpolar molecule, which is what this is a molecule that is symmetrical. I knew I was going to misspell that. Symmetrical is two ends. All the way around. Okay, so what that means is, sorry about that. I don't want the arrow. Okay, what that means is if I were to split this molecule in half, let's say I split it this way. Let me do a line. I'm going to draw this in, let's do orange. Okay, so let's say I split the molecule in half like this. The top is exactly the same as the bottom. So they're not different. Okay, I'm going to erase that line. Let's say I draw the line this way. This left side is the same as this right side. So again, not different. Let's say I split the molecule this way. Okay, this side, same as this side. So it's symmetrical no matter how you cut it, and that will make it a non-polar molecule. Okay, polar means that if I cut it in half, there's a difference on the top than in the bottom. For example, we are a polar being because our head is different than our feet, right? A tree is a polar being because its top is different than the roots, okay? But this molecule is symmetrical all the way around, and so that is called a non-polar molecule. So sometimes these bonds are called non-polar covalent bonds, okay? Okay, the last type of chemical bond is called a hydrogen bond. This is number 3. Okay, and a hydrogen bond is when you have different molecules that have different charges that are attracted to each other, and one of the molecules has hydrogen. So I'm going to write this down. When two atoms are attracted to each other because of differences in their charges, okay, just like an ion, just like an ionic bond. And one of the atoms has hydrogen. Okay, that's a hydrogen bond. I'm going to show you an example. Okay, so I'm going to draw, the example I'm going to use to show a hydrogen bond is water. And do you guys know what water is? Yes, it's H2O. We learned this in kindergarten. You ask any kid and they always know H2O is water. What this means is we have 2 hydrogens and 1 oxygen. Okay, so I'm going to draw a Bohr model of water. Okay, now that we know how to draw a Bohr model, we're experts at Bohr models. So oxygen, I got to go back to the periodic table real quick. Let's see, oxygen, the atomic number is 678. So it's 8 for oxygen. Okay, so we've got 8. Okay, what do I have here? A line? No. Okay, 8 protons in the nucleus, 8 neutrons in the nucleus. Okay, oxygen was 8. Okay, so it's going to have 2 shells. So we've got 1 shell and then 2 shells. I'm going to make that a little bit smaller and scoot that over like this. Okay. Okay, and then I'm going to make its electrons pink. So we've got 8 electrons. 1, 2. I'm going to put it here. 3, 4, 5, 6, 7, 8. Okay. So in this outer shell, it needs 2 more to be full. So it's going to bind to 2 hydrogens. So I'm going to make the hydrogens teal. And I'm going to make one hydrogen here. And this is covalent bonds. Okay. So here's a hydrogen here. And we've drawn hydrogens already. We've got one proton in the nucleus, one neutron. This one has one proton. Oops. One proton in the nucleus, one neutron. And then I'm going to make the water electrons orange. And so I'm going to draw that here. It's sharing. Okay, so here's what water molecule looks like. And it always has this Mickey Mouse shape. So water is always in this configuration. There is a reason for that, which I'm not going to get into here. But it always has this Mickey Mouse shape. And it's always got these ears. And this is the Mickey Mouse head. Okay, and so this right here is a covalent bond. So I'm going to write that actually. Okay, so this is a covalent bond because they're sharing electrons. Okay, and earlier I was talking about polar, nonpolar. Water is a polar molecule. I'm going to write that here. Water is a polar molecule. And that is because if I split water this way, so if I split water this way, oops, I wanted to make a straight line. Here we go. If I split it this way, this is different than this. Okay. So it's still doing the arrow. I don't want the arrow. I just want the line. Okay. If I split it this way, it is the same on both sides. But because I can split it in a way that makes the top different than the bottom, it is called polar. Okay. And so this is a polar molecule. And here's the thing about polar molecules. They have a difference in charge. So this part of the Mickey Mouse head has more electrons. You can see that all the electrons are on the oxygen pretty much. The hydrogen, here's the hydrogen, there's not electrons. All the electrons are stuck to the oxygen. So when I split this molecule in half like this side of the molecule is more negative because it's the oxygen. This side of the molecule is more positive because there's less electrons. Okay, so I'm going to draw it like this. This is This is a way that we write partial. It's like this weird squiggly line. We say this is partially negative. That was supposed to be a negative sign. It's like this little squiggly with a negative, which means that this molecule is partially negative on this side and partially positive on this side. So this is going to be a plus sign here. Okay, so where the Mickey Mouse ears are, it's positive. Where the Mickey Mouse head is, it's negative. So this is a polar molecule because the top is different than the bottom and there's a difference in charge. And these are hydrogens. So I'm going to show you hydrogen bonding now. So what I'm going to do is I'm going to draw a whole bunch of water molecules. Okay, so I have a cup here full of water that I've been drinking all day. And there are lots of water molecules in my cup. Millions and millions of them. So I'm just going to draw a whole bunch of water molecules right now. Okay. So what do I have here? Line. Okay, that's good. I'm not going to draw them very good because I need to draw a whole bunch of them, but I'm just going to draw them like this. So here's one Mickey Mouse head. Here's another Mickey Mouse head. Oops, that doesn't look like a Mickey Mouse head. Hold on. That is just not good. Okay, so we got the Mickey Mouse head and the Mickey Mouse ears. Okay, Mickey Mouse head, Mickey Mouse ears. I'm going to put Mickey Mouse head here, Mickey Mouse ears. Okay, so what I want you to envision is in a cup of water, you have all these water molecules moving around, okay? And there's a partially difference in charge. Where the hydrogens are, this is more positive. Where the oxygen is, this is more negative. Where the hydrogens are, this is more positive. Where the oxygen is more negative. The hydrogens are more positive. The oxygen is more negative. Same here. This is the negative side, positive side. So in between the water molecules, you have this attraction right here. This positive and negative are attracted to each other. Okay? And these positive and negative are attracted to each other. So waters are sticking to each other because there's this attraction. So this attraction right here is called a hydrogen bond. So let me draw that here. Here's arrow. Whoops. So right there is the hydrogen bond, where there is an attraction between a positive and negative, and one of them is from a hydrogen. And these hydrogens are what's making it a hydrogen bond. So the hydrogen bonds are in between the water molecules, where the covalent bonds are within the water molecules. Okay, so I'm going to write that down. This is important. Hydrogen bonds are between water molecules, and covalent bonds are within water molecules. Okay? And so that's it. That's all I got for today. Okay. Have a nice day, and I will see you next time.